With Bernoulli's principle, we're going to be talking about conservation of energy and conservation of flow within the motion of a fluid. So here we have two different types of fluid motion, laminar flow and turbulent flow. Laminar flow is what happens when you have very smooth, streamlined laminar flow. So basically, if you were to put something in the water and draw the path of the water, it would be a very smooth path. Here we've got an airstream. You have a bunch of air moving through a wind tunnel, and you add some dye or something into the air fluid, whatever's flowing, and you can just see the motion of the water. And for the most part, it's quite smooth and undisturbed. But every once in a while, if you were to, say, put an object in the middle of that flow, then that air would have to be diverted, and then downwind of that object, you get a bunch of eddies, some turbulent motion. You can see that quite well here in this area. It's not very smooth anymore. It's quite disturbed and shaky. So that's where turbulent motion comes from. Now, we are going to be dealing with laminar flow. We're not going to deal with turbulence in this class. That's just a far more complicated problem. So we're dealing with laminar flow then. Now, when we talk about the mass of a fluid, that's really hard. We find that it's more useful to talk about the density. Likewise, when we talk about the velocity of a fluid, sometimes it's more useful to talk about something called the mass flow rate. How much mass is flowing by a certain point in a given amount of time. Now, the mass flow rate that passes a given point per unit time at any 2 points must be equal. Let me show you what I mean by in this next slide, and then I'll come right back. So we have a tube where the diameter decreases. The diameter of the tube decreases. Here you have a certain amount of mass that is moving in a given amount of time. Well, in the narrower part of the tube, you must have the same amount of mass pass through a point in the same amount of time. That's how laminar flow works. The amount of water going in has to equal the amount of water going out in the same amount of time. So if we do that, if we take the mass flow rate as the change in mass over change in time, and we break down mass into density times volume, this is what comes out of it. Density times area times velocity has to be a constant. So one end of the tube, take the density, multiply it by the area of the tube times the velocity of the fluid through the tube. That has to equal the density of the fluid times the area times the velocity through a second part in the tube. So that relationship, which I can rewrite here, that product of those three numbers has to be the same on both sides. Now, many times the density doesn't really change. We get a particular fluid that's not compressible, is what we call it. Basically, you send a fluid through a pipe, the fluid will not change its density as it flows. So we can often just eliminate that term, and it simplifies to the product of area times velocity has to be a constant. This is known as the equation of continuity, that the area times the velocity is a constant in the motion of a fluid. Okay, that is an equation that helps us know a little bit more about the motion of the fluid itself. Let's talk about a conservation of energy here for Bernoulli's equation. All right, you have a fluid that can change its height. Now we can look at the amount of work that's done by this fluid as it changes its height. Let me do this. So we have kinetic energy plus potential energy has to equal kinetic energy. Let me leave a little space here. Kinetic energy plus potential energy at a second point. But this is just talking about kinetic and potential energy. What if there are other forces going on? Well, then we have to account for the work done by that force. So force 2 times d on the right, force 1 times d on the left. And kinetic energy is just 1/2 mv squared. Potential energy is just mgh. And it's the same thing on the right side. Okay. But once again, we don't want to talk about mass. This is a fluid, so mass of fluid is kind of hard to deal with. We're going to change it into density. How? We're going to divide everything by volume. And that's on every term. Well, on the left, that means you get force 1 times distance over volume is just area times distance. Look, those distances cancel out. Plus 1/2 of the density times velocity 1 squared plus density times g times h1. And then on the right, you get F2d over area times d. That's your volume again. Distance disappears. Plus 1/2 density times v2 squared plus mgh2. Sorry, not mass. It's got to be density because it's mass divided by volume. Okay, so those two work terms that we had are just force divided by area. Well, what's force divided by area? That's just pressure. So now we have a conservation of energy equation for a fluid. Now if we go back to our slides, you'll see that that is exactly the equation that we have on this slide. This is Bernoulli's equation. It talks about the work done on a fluid, conservation of energy, due to differences in pressure, differences in velocities, and differences in heights. So one thing that's very important to note here is that as the speed goes up, that means that the pressure goes down. What does that mean? The velocity goes up, so your kinetic energy term goes up. Therefore, either the height has to decrease or the pressure has to decrease. But if you have a constant height, then that means pressure definitely has to decrease. But you have a relationship where you can see what happens to your pressure based on what your velocity and your height are doing. Now here's a very important application of Bernoulli's principle. We can actually find the speed of a fluid coming out of a spigot in an open tank. How? Well, you have Bernoulli's equation. I'm going to make it complete, put all the terms there. But the atmosphere is exerting a pressure here, and the atmosphere is also exerting a pressure here. It's the same atmosphere, same pressure, therefore that term goes away. Also, at the very top of your tank, you have no velocity, therefore your kinetic energy term goes away. And so that's where this equation at the top of the screen came from. So you have your kinetic energy at the bottom plus the potential energy at the bottom has to equal the potential energy at the top. And when you solve for your velocity, you get this equation, which we call Torricelli's theorem.